Okay, so in this video clip, we're going to use Google Colab and we're going to load in this R command, which allows us to run R in the Google Colab. And so long as I have this double percentage sign and R, we can then invoke and apply and, and use R commands in the Google Collaboratory. That's quite a handy feature because sometimes we have snippets of code and packages available in R that actually could be quite useful. So, okay, we've installed this derivative markets package and we've made it available in this environment. And this package is on the R CRAN repository. And Professor Robert MacDonald, who's author of Derivative Markets, has made available this package. The really nice package with lots of functions that are generally useful for option pricing and for more structured type finance. Here we output the Greeks, the Black Scholes Greeks, for both the call and the put by using these simple commands here. So that's quite convenient that we have a way of outputting quickly Greeks. We can adopt our functions so that we can consider different strike values. So we initially had 100 and we allow for 90, 100, 110. And for the delta and the call, we estimate, or for the delta and the call, we estimate using these three different strikes, the delta and the gamma. And that's, again, quite useful combination. Then if we wanted to consider a series of different stock prices, we could set that up in an array. So starting at 10, going to do 100 in steps of 5. And then we can plot out using a double loop here. We can plot out the delta, gamma, vega, theta, and rho. Again, that's a nice little graph. We could copy this image and then paste into Word or paste into Excel or whatever format, PowerPoint. If we change the dividend yield here, note that K is the exercise, V is the volatility, R is the risk-free rate in the Black-Scholes model, T is the maturity, D is the dividend yield. If we change that to 5, we get a different set of output. Notice that there's a theta range here for the call that's actually positive. It's normally negative, but here we have a positive range. And that's something that is expected in this type of analysis. Okay, so I'll change back to 0. So later on when we make comparisons, both Python and R code can be compared directly against each other. If I want to use a little bit better graphing so that the background is a little bit richer and we have a kind of grid environment, I can use the ggplot2 in the tidyverse suite and also use the plier syntax for pipe operators. So below here, we will run some code, but notice that we're estimating the Greeks. We're using a ggplot function. We're using also facet wrap. And we have the name of each of the outputs. We have both call and put in each small graph here in the facet wrap. That's quite convenient. Again, if I change to 0.05 for the dividend yield, we'll see that the theta becomes, here it has a negative range. That's what we would expect. But if the dividend yield is 5%, we get a positive range. Okay, and that's allowing for the possibility that as the dividend increases, that changes the relationship between time, the maturity, and the value of the option is a little bit nuanced, right? So typically, as we increase the time period, the value of the option goes up. But if the dividend is quite high, that mightn't be guaranteed. Okay, so following this hyperlink here, I took some code, made some small changes. I follow in line with Clint Howard's GitHub. Might check this out. It's quite a good GitHub. Lots of interesting stuff in there. We import some of the standard library, pandas, matplotlib, numpy. And then we define, again, this is from Clint Howard's GitHub. We define the functions here for the Greeks, and we include, but in this instance, we're going to include the dividend yield, and that's important so we can make comparisons. And then we run for a specific set of parameter inputs. Again, Q is equal to 0. And we can compare these values here by just putting to one side, right? And then go back and have a look at the call output, and we can see they mirror, right? So it's quite similar. The gamma is the same. Vega is the same, except here we divide by 100. Likewise with theta, we have our row, we divide row by 100, so we get the 0.53 here, otherwise the same. Theta, if we take the theta and divide by the number of days in a year, 365, we go from 641 to 0.01, and that's the same value that we have here. So McDonald's theta is a daily theta, okay? So that's worth noting. We can go down a little bit further. We use the ggplots and facet wrap. That worked extremely well and quite aesthetic. We can output then the values for the put option, and we should get 557. And let's compare those, right? So we come back up to using the same parameter inputs as before, right? We now have 557, 557. The delta is negative 3636. Gamma is the same. Theta is the same. This is the daily theta, 54. And the row, we divide this by 100 and we obtain the value here. So both are consistent. Again, coming down, we have outputted the Greeks, and if we want to define a set of values going from 0 to 100, and map the Black Scholes. So we're considering different stock prices, and the exercise is 100. That we can make the comparison with what we obtained in the R environment. So we saw something similar, and that was just the premium, right? So we have the same output for the same parameter inputs, basically, right? And the series that we obtained here, right? If we take a slightly more in-depth look. Okay, so we have an array here for the stock price that we put in for both the call and the put, and we're going in steps of, I'd say 1. So just to see that, we could print the vals, VALS underscore call. So print vals underscore call and run again. And we would see just underneath here, we get a range of values and it's going up in steps of 1. We could do it in steps of 10. That would leave us with 20 values, and try again. And you can see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that would have been 20 in all. But to go in steps of 1, that would be sufficient to run that, and we get that output. We'd have then 200 outputs. Okay, so I'll run that again, leave this out. So we get a nice clean diagram, and as we saw before, that's consistent with the output here from the derivative markets package. Last then is to get a full suite of output for the Greeks. And again, we're using the same parameter inputs as before. And if we care to make the comparison then against the, or let's see, can we, okay, that disappeared. Okay, so we have to undo delete cell and then run again. And we get some output. And then if we want to make the comparison, we just post up here on the side, all across, and then take a look and compare it against what we had observed before. So the deltas are quite consistent. The gamma for the call and the put are the same. That would be true. The vega will be the same. Again, we observed that for both call and the put. The row are consistent. The range of values we're observing is the same. Keep in mind, we divided by 100 to get the derivative markets row, and similar for gamma. Or for vega. And then the theta range here, in this instance 0, 5, let's convert back to 0. And then when we compare the dividends here, we said that the dividends that we've incorporated in are values that we allowed for here. So 0% dividend would appear. And when we look at the values we have here for theta, okay, so it would appear that the values we have here include 0 dividend here. For the Python, we have to change dividend to 0 and then execute. And then let's compare the thetas, and we can see the thetas are again consistent with what we have here and here. If we change this to 0, 5 and run again, and change this to 0, 5 and run here, we can make the direct comparison. And yeah, the shapes are very similar. The values, again, we have to divide this by 365. This is the daily theta, this is the annual theta, but the shapes are consistent. And we have a positive range for the call theta, right? We get a positive, negative, and then goes positive. Okay. Okay, so that's a good comparison between the different packages and the graphing capability of both, and being able to integrate in R and Python together, obviously quite useful.